Hi, this is Module 22 of Two-Dimensional Dynamics, and today's learning outcome is to go ahead and solve a dynamics engineering problem involving rolling wheels. Let's first look at a summary of what we've done in the last couple of modules. We looked at a wheel rolling on a fixed straight line. We found the acceleration of the center of the wheel and the acceleration of the point of contact. We then looked at a wheel rolling on a fixed plane curve, and we found the acceleration of the center of the wheel and the acceleration of the point of contact. One thing I'd like you to note that as the radius of curvature for our wheel becomes infinity or approaches infinity, the relationships approach the fixed straight line condition because the wheel as rho approaches infinity is just the straight line condition. And so if I look at my equations here for the acceleration of the center of the wheel as rho approaches infinity, this term goes away, and we see that these two equations match. For this acceleration of the point of contact, as rho goes to infinity, this term goes away, and I get r theta dot squared in the e normal direction, which will be up, which is equal to minus theta dot squared r in the j direction. Since j is defined as down, negative that will be up, and so this equation and this equation are the same. Okay, let's go ahead now and solve a problem. One thing I wanted to mention was back many years ago when I was doing my undergraduate studies in engineering, one thing I remember is the instructor kept saying the center of the wheel is your friend. And so that's often the case. You can usually find what's going on kinematically at the center of the wheel. And so remember that, and that's always a place to go from knowns to unknowns. And so it's just a little tip. I always, as I say, it's something that stays with you over the years. The center of a wheel is your friend. Okay, so we want to find the relationship between the angle phi and the angle theta here. So the angle phi is the angle at which the center of the wheel rolls around this inside cylinder. So we got this cylinder or this wheel rolling around a fixed cylinder, and so as that does that motion, we have the center of the wheel moving at an angle phi, and at the same time, the wheel is spinning with an angle theta dot, or an angle of rotation theta. And we want to find the relationship between those two angles. And so what we can do is, again, looking at the center of the wheel, which is our friend, I can say, okay, V of C is equal to, if I go from the center of the fixed cylinder, where the velocity equal to 0, down to the velocity of the center of the wheel, I get the radius is going to be big R minus little r. So this is big R minus little r. And the angular velocity is theta dot, or excuse me, phi dot. And that's going to be as phi is going counterclockwise, that means that the velocity of the center is going to be E tangential. Similarly, we can look at the velocity of the center of the wheel from the perspective of the point of contact here on using this spin velocity, which is theta dot. And so we've got the velocity of C is also equal to little r, which is the radius from I to C, times theta dot E tangential. And so we have two different expressions for the velocity of the center of the wheel, including the two angles we're interested in, which is theta dot and phi dot. So therefore, we can set those equal, and we get big R minus little r phi dot equals r theta dot. Therefore, if I integrate that and I use as my datum phi equals 0 at time 0 and theta equals 0 at time 0, when I integrate, I'll get the relationship that theta is equal to big R minus little r over little r phi. And so that's our solution for finding the relationship between the angle phi and the angle of rotation theta. And I'll see you next time.